This video covers section 5.2, checkpoints 47, 49, and 63 as the result of the Poll Everywhere poll on which checkpoints to make a video from that we did on October 24th. So, let's look at problem 47. It says sine of beta over 1 minus cosine beta is equal to 1 plus cosine beta over sine of beta. And since we have a 1 minus cosine, that looks like something that we could probably turn into a Pythagorean form by multiplying numerator and denominator by 1 plus cosine beta. So let's go ahead and do that. 1 plus cosine beta over 1 plus cosine beta times sine of beta over 1 minus cosine beta. And we leave the right-hand side alone at this point. Now, you should recognize at this point that 1 plus cosine beta times 1 minus cosine of beta is going to be 1 minus cosine squared beta. Let's leave the numerator undistributed, so let's don't do anything with it yet, because it may come in handy that way. We recognize at the bottom is a Pythagorean form because cosine squared beta plus sine squared beta is equal to 1. So if we subtract cosine from both sides, we get sine squared beta is equal to 1 minus cosine squared beta. So we can substitute that back in for our denominator, and at that point we get 1 plus cosine beta times sine beta over sine squared beta is equal to 1 plus cosine beta over sine beta. Well, but we have sine beta there and sine squared beta here, so we can cancel the squared, and what we're left with is 1 plus cosine beta over sine of beta is equal to 1 plus cosine beta over sine beta. So now we have the same thing on both sides, so we have proved that identity. Again, all we had to do was get that Pythagorean form in the denominator. The next checkpoint that we're looking at is number 49, which starts out with tangent alpha cubed minus 1 over tangent alpha minus 1 is equal to tangent squared alpha plus tangent alpha plus 1. Now, we have some choices on how to approach this one, but before we do, there's an important thing that we need to go back and look at from algebra, and that's called the difference of two cubes. And in algebra, we should have learned that something like x cubed minus y cubed is equal to x minus y, x squared plus xy plus y squared. Okay? That's the difference of two cubes. You can Google difference of two cubes and you'll see that show up with a proof if you like. Now, we see that tangent cubed alpha minus 1 fits this pattern. We can substitute in tangent cubed alpha minus 1 is equal to tangent alpha minus 1 tangent squared alpha plus tangent alpha plus 1. Okay? That fits the form of the difference of two cubes. So if we replace the numerator of the left-hand side using the difference of two cubes, we get tangent of alpha minus 1, tangent squared alpha plus tangent alpha plus 1 over tangent alpha minus 1 is equal to, and now I'm going to have to write this down below, tangent squared alpha plus tangent alpha plus 1. Now here's where we have a choice. We can say, oh, well those cancel, in which case these two pieces are identical, so we've proved our identity. Or we can multiply both sides by tan alpha minus 1, and we get tangent alpha minus 1, tangent squared alpha plus tangent alpha plus 1 is equal to tangent squared alpha plus tangent alpha plus 1 times tangent alpha minus 1. And again, both sides are the same. Either approach is okay. The only reason that I really talk about this second approach is so that this problem looks a little bit like working on both sides of the equation. Again, either one is fine. They're both perfectly good solutions. It is important, however, that you remember that difference of two cubes. If you don't have that on your reference card, I suggest that you put it on there now. Again, you can Google that, find difference of two cubes, and add it to your trig reference card. The next checkpoint that we want to look at is number 63, and it's tangent to the fifth x is equal to tangent cubed x secant squared x minus tangent cubed x. Now, this seems kind of funny because we're taking something that is simple and making it a lot more complex. However, this is a technique that you'll use quite a bit in calculus because this gives you a form that you can work with in some of the tools that you learn in calculus. This would be a difficult thing to work with, but interestingly enough, this would be a lot simpler. So in some cases, you want to complicate it in order to make it easier to work with. So here we're going to use one of the techniques from the Pirates Code. We're going to look at what we have and then what we want. And we notice that we have this tangent cubed that we want as a result. So let's take tangent to the fifth and split it into tangent cubed x and tangent squared x. The two powers, the exponents, have to add up to 5, so if we factor out a tangent cubed, then we're left with a tangent squared to make tangent to the fifth. But this is another Pythagorean form because 1 plus tangent squared x is equal to secant squared. So that says tangent squared x is equal to secant squared x minus 1. I can substitute this into there now, and I get tangent cubed x secant squared x minus 1. And then if I just distribute the tangent cubed, I get tangent cubed x secant squared x minus tangent cubed x is equal to what I was looking for. Tangent cubed x secant squared x minus tangent cubed x. So it's really just a matter of looking for what you want and then separating the powers of tangent into two pieces that you can manipulate into that. Now, for those of you that have survived to this point, I have an opportunity for you. If you will go to problem 74 on page 367 and answer that question with justification, so in other words, explain why your answer is true, and email that answer to teddy.wyatt@tulsatech.edu. Make sure it has your name in case you're sending from an email address that I don't recognize, so tell me who you are. And if you answer that correctly, then there will be a 5 bonus point certificate for you after you've done that.